Hello everyone, and welcome to this talk about polytopes, lattices, and spherical codes for the nearest neighbor problem. So this talk will be about nearest neighbor searching. So for this problem we are given some data set of points in some vector space. So in this case they are indicated by these black points on the slide. And so we want to store this data set in a data structure such that given a query point later, we can quickly identify the nearest neighbor to this query point in the dataset. So if we look at the Euclidean distance, then for instance this blue point here would be the nearest point, and we want to find it, and then ideally faster than going through the entire dataset. So one solution you can think of for solving this problem and for storing this dataset efficiently would be to first compute the Voronoi cells of the dataset. So in this case, this partition of the space indicates which point in the dataset is closest to each point in this entire space here. And so if we can store these Voronoi cells efficiently and query them efficiently, then given a query point, we could first look up like in which Voronoi cell it is located, and then from this we would conclude, okay, the point in the dataset in this Voronoi cell must be the closest one. So in that case, we would quickly find that, okay, this point P here must be the closest, the nearest neighbor in the dataset. But so one problem with this, with using Voronoi cells, is that, okay, this works well in low dimensions, but in high dimensions, like storing the Voronoi cells and also querying them, like finding out in which cell you are out of all these cells, this seems to be quite ineffective. So we need different solutions. Okay, so first, for this problem, for the rest of the talk, I will assume that the data set is normalized and it is uniformly random. So that means that, so normalized means that all points in the data set have the same norm, the same distance from the origin. And all these points are kind of scattered uniformly around the sphere that is indicated by this black circle here. And so given such a uniform dataset, we want to store it, and then the query point is also assumed to be uniformly random on the sphere. And then again, we want to find the nearest neighbor on the sphere. And now, because everything is normalized, the distance does not really matter. It's all like the nearest neighbor in one distance is usually the same in all distances. So in this case, the Euclidean distance, the closest point would be this blue point P again. But also you can look at, for instance, the angular distance, like the point that has the smallest angle with the query point would also be this point P. And for the rest of the talk, I will also talk in terms of the angular distance because it's a bit more convenient to work with. And I will denote the angle between the query point and the nearest neighbor in the dataset by this parameter theta here. So theta is the target angle of the query and the nearest neighbor in the dataset. So again, so just to clearly state the model that I'm assuming here. So the dataset consists of n uniformly random points on a d-dimensional sphere. So n is the size of the dataset and d the dimension that we are working in. The query point is some random point on the sphere as well. So the dataset is random, the query point is random. And the objective after the preprocessing is to find the neighbor P which has an angle smaller than theta from the query point. And so a naive solution would just be to go through the entire dataset one by one and see if any of them has a smaller angle than theta with the query point. And this would take big O of n time and big O of n space for storing the entire dataset. So one method which does seem to work quite well in higher dimensions as well is locality-sensitive hashing. So the idea of locality-sensitive hashing is to use hash functions to partition the dataset in hash tables. So we split the sphere into regions and we store nearby points in the same hash buckets basically using these hash functions. And then given a query point, we would look up in which hash region this point would be, and then we retrieve only the points which are in the same region, and we check if any of them are nearby to the query point, like if any of them are near neighbors. I will get to that later, like how it works. So if we use this locality-sensitive hashing framework, then commonly we are interested in two quantities, namely the collision probability for nearby vectors. So P1 here denotes the probability of getting the same hash value if two points are at a small angle from one another. And P2 denotes the collision probability for random factors, like if this point P here is not the nearest neighbor, but some random point from the data set, like what is the probability of getting the same hash value, so ending up in the same hash bucket as the query point. And so if we would be able to compute this quantity P1 and P2 here for a given target angle theta, then we can compute the hash family exponent rho as the ratio of these logarithms. And from that we can compute the query cost of like lookout extensive hashing as big O of n to the rho time, query time, and n to the 1 plus rho space. And so this is kind of folklore. This has been used many times, this lookout extensive hashing framework. And so I will not go into the details of how you get these complexities here, but like we are interested in these quantities P1, P2, and then the exponent rho. Okay, so one way to do lookout extensive hashing is the following, and this kind of captures most approaches that have been considered so far, at least for the angular distance. So we start with this data set and this query point on a d-dimensional sphere. So what we do to partition is we first project onto a lower dimensional sphere. So in this case it's indicated by this smaller circle in the middle here. We should imagine this to be like a lower dimensional sphere, not a smaller sphere, but a lower dimensional sphere. So we first project onto this. So the projections are indicated by these dashed lines here. And note that if you project from a higher dimension to a lower dimension, then like for instance, angles between vectors, they are not perfectly preserved because you are going to a lower dimension. So you are losing information here. And so that is kind of indicated here by the small shifts in the points on the lower dimensional sphere. Like they are not exactly projected, like they're kind of shifted, like the pairwise angles are not perfectly preserved anymore. Okay, so you apply some kind of dimension reduction, like you project onto a lower dimensional sphere. And after you do this projection, so you can also get different shifts after you project with a different random projection. And after you project, then you partition this lower dimensional sphere into regions, because like originally we started with a very high dimensional sphere, and it's kind of hard to find nice ways to partition this high dimensional sphere. And maybe it's easier to partition this low dimensional sphere into regions, like because it's easier to like see what's going on in like 2, 3, 4 dimensions, etc. And so to partition this low dimensional sphere in regions, we will assume the following model, that we take a spherical code, which is indicated by these 4 green points here, and then we look at the Voronoi cells induced by these 4 points. So in this 2-dimensional case here, you get a partition into 4 regions of the circle here, and they are the 4 regions that you get from this hash function. And so then the preprocessing would consist of making a table with 4 hash buckets corresponding to the 4 regions, and then for each data point you store them in one of these 4 buckets, and then given the query point you would look up that is also in the top left bucket in this case, and then you would see that okay, there's only one other point in the data set in the same bucket, this black point, which is not grayed out right now, and we would check it to see if it's the nearest neighbor or if it's near enough. And in this case it's not the nearest neighbor because the blue point before projecting down was actually closer and had a smaller angle. And of course, besides the random projection, you can also rotate your spherical code, or you can somehow shift it a bit, and then you also get kind of a slightly different partition into regions. And so this whole this probability analysis is based on the randomness of the partitions and the etc. And so in this case, for this partition, you would actually find this blue point in the same bucket as the query point, and you would find the nearest neighbor with this approach. And so what we are really interested in here, because the projections are kind of straightforward, like you just apply a Gaussian to go to a lower dimensional space. So what is really the interesting question here is, how do you partition this low dimensional space into regions? Like how do you choose these spherical codes to partition the space? So that's denoted by this big C here. Okay, so just to skip immediately to the main result, which is kind of phrased informally here. So the main result of the paper or the main analysis is based on like, okay, given a spherical code, can we somehow compute like the suitability of using this code for local sensitive hashing? Like, what is the parameter rho, for instance, that you get from this? And to compute rho, you need to know the collision probabilities P1 and P2. And so here this theorem states that given like any spherical code, and this induces some kind of hash function where you first project and then you assign hash values based on the Voronoi cells of these code words. Then for any target angle, you can express the collision probability P1 in terms of orphan probabilities of a multivariate normal distribution. So this is the probability that a multivariate normal vector has all positive entries, given that it's from this multivariate normal distribution with it's centered around the origin, but the correlation matrix or the covariance matrix is not the identity. So it's like a kind of skewed multivariate normal distribution, and you want to know what is the probability that from this distribution you get something which is in the positive quadrant, positive orthant, basically. So the dimensionality of this probability, like the dimensionality of this Gaussian, depends on the code size C, as you can see here. Like the size of this matrix sigma is 2C by 2C. And the collision probabilities P2 are actually quite easily expressed in terms of volumes of Voronoi cells induced by this code. So the takeaway of this slide is basically that given any spherical code, we can now compute the performance of it, like what is the exponent rho that you get from this. So just to illustrate this with an example, so probably the simplest way to partition to do this approach is to go to like a one-dimensional projection or a two-dimensional projection where you partition only in two regions, where the 2 points, like the forming spherical code, are two opposite points on this sphere. So that partitions the low-dimensional sphere into two regions. And this has been studied long ago. So in terms of this framework, you get that the collision probabilities are, okay, P2 is just 1/2, and P1 is like 2 times this orphan probability, where the correlation matrix has this shape of like 1 cosine theta 1, and some scale of 4 that you don't really care about. And there's this ancient result from the 19th century, actually, from 1899, from Shepard, which says that if sigma is of this form, like 1AA1, for some parameter A, then the probability that such a multivariate Gaussian is all positive, lies in the positive quadrant, is pi minus r cosine of A over 2 pi. And this gives you the well-known hyperplane hashing result of Sharika from 2002. But actually, like this analysis, if you can call it, actually dates back to like already 1899. It's pretty old result. Kind of neat. Okay, so that's what you get in one dimension. The slightly harder case that you can think of is what happens when you go to a two-dimensional projection. So you take your d-dimensional sphere, your data set, and you project onto a circle, basically, like a two-dimensional sphere. And then you partition this into regions induced by some spherical code. So what is the simplest way to use a code in two dimensions is just to, or the nicest way that you can probably think of is to use a regular polygon. So if you use 2 points, then again you just get the antipodal code, which I just discussed before. If you take 3 points and you take a regular three-gon, then you just get a triangle. So this would partition the circle into 3 regions. You can take 4 regions, you get a square, etc., a pentagon, a hexagon, and for instance, with these 6 points, you would get this partition of the circle into six regions. And so you can wonder, like, what is the ideal code size to use if we use this project-and-partition framework where we project onto a two-dimensional sphere. So in this case, we get this shape for the correlation matrix. So explicit formula for sigma here, which is some scalar times this tensor product of these two matrices, where the left matrix has this parameter theta in it, like the target angle, and the right one has the parameter c in it, like the size of the polygon, like the, yeah. So in this case, again, there is this very old result. It's about 50 years old now, this result, from Cheng, 1968, which says that, okay, if you have a correlation matrix of this form, like 1A, A1 tensor 1B, B1, then actually you can express this orthogonal probability explicitly, like you get a closed form expression like the one that's given here. And this, I mean, it's not such a nice formula, but it's an explicit formula in terms of just A and B. So that's pretty nice that you can get a closed form formula here. I mean, these orthogonal probabilities, they quickly become pretty complicated and you don't get closed form expressions anymore. But here, at least, like in 2 dimensions, you still get a nice closed form expression here. And so you can just use this result from Cheng to get explicit values for P1 and P2 for using regular polygons. So in this case, you get these expressions. So P2 is again very simple, but P1 is now this messy thing here. But okay, it's very explicit in terms of just the parameter c, the size of the polygon, and theta, like the target angle that we are interested in. And so it's just a formula where you can just plug in values of c and theta and see what happens. And then you get explicit values for P1, P2, and also for rho. So you can wonder again, like, what is the optimal code size? Like if I just choose theta is pi over 4 or pi over 3 on the left and the right, and I just plot these values for different values c, then we get these curves here. You can see that the minimum is actually at 3, so a code size of 3, so like the triangle would be the best to use. And this is the case for any angle that you can plug in here. So using a triangle is actually optimal if you project onto a 2-dimensional sphere and then partition into regions. And this is actually also better than the antipodal code, which would correspond to using 2 points to partition a 2-dimensional sphere into 2 regions. So that's this corollary 3 from the paper. Okay, I will not phrase it explicitly, but what it says is that you get an explicit expression for this rho here. It's just this ugly formula here, which is actually better than what you get from the antipodal code. And also there's no order terms here, no hidden order terms. This is just exactly what is rho. There's no hidden dependence on d that I didn't mention here. This is just exactly the parameter rho, and you can also get exactly the parameter P1 and P2. So that's pretty nice. And again, you can ask like what happens when you go to higher dimensions, but like I said, when you go to larger codes and to higher dimensions, this quickly becomes too complicated to get closed form expressions. So, but okay, so in 3 dimensions, you can wonder like what is the nicest shape to partition the sphere. So what are some nice spherical codes in 3 dimensions? So for instance, you can use the tetrahedron, like these 4 points, like roughly like this, or the octahedron with 6 points, icosahedron with 12 points. I mean, there's many nice shapes in 3 dimensions, like the platonic solids, etc. You can wonder like, okay, what's the best shape we can use to partition like a sphere? And okay, for instance, for the tetrahedron, we get this explicit form for the correlation matrix, for which we are now interested in the positive orthogonal probability. It looks kind of nice, this matrix, like the right matrix is just 1 and 1/2, and the left one is as before, but even for this kind of nice-ish matrix, it's already seems very difficult to get closed form expressions for the orthogonal probability, like the multivariate Gaussian orthogonal probability. So that's actually an open problem, like finding closed forms for this matrix sigma, like the orthogonal probability, but also for the matrix sigma that you get for other polyhedra. Like this is for the tetrahedron, but you can do the same for other polyhedra, and you get different matrices you're interested in, like what is the positive orthogonal probability. And yeah, getting analytic expression seems to be very hard starting at dimension 3 already. But okay, you do get like explicit expressions for P1 and P2, and you can just evaluate them numerically, and then you do just get numbers, and you can just compare the numbers. I mean, you don't get nice formulas, but you get at least something to compare. And here you can see an overview of some three-dimensional codes. So you can see that the tetrahedron actually achieves the smallest values rho here. The bold face, that means that it's the smallest for this target angle. And the codes are sorted by the code size. And so you can see that actually a small code size of only 4 points is actually the best that you can do in 3 dimensions for any target angle, basically. You can also do the same exercise for 4 dimensions, and I mean there are not so many nice shapes out there that we know of in 4 dimensions, but these are just a few of them. And here you can see that okay, if the target angle is very small, then it works best to use the 16 cell, like the cross polytope in 4 dimensions with 8 points. And if the target angle is pretty large, then actually only using 5 points is better. So if the target angle is small, then you want to use a more fine-grained partition of the 4-dimensional sphere into regions. And between parentheses like S4, O4, C4, A4, and D4, that means they are families of, they are part of a family of spherical codes like the simplices or orthoplices, the cubes, and the root lattices A and D. And the O4 is also just a cross polytope, like related to cross polytope hashing. Also for dimensions 5 and 6, again, you can just do this exercise and you see that cross polytope is the best in 5 dimensions, and in 6 dimensions, again, cross polytope is good for large target angles, and for small target angles, actually, this 221 polytope, which is related to the E8 root lattice, seems to give you the smallest values overall. And this is also a graphical depiction of these results. So on the vertical axis, you have the query exponent, like what you really care about in minimizing this, because it determines the time complexity. And on the horizontal axis, you have the dimension that you're projecting down into. And then you see for different families, which are the different lines here, that for most of these families, the query exponents go down, except for the hypercubes, which are not so nice to use. And the cross polytopes, like the green curve here, you see that it actually achieves the lowest query exponents for this target angle pi over 4, starting at dimension 4 already. And also if you take target angle pi over 3, then the picture changes a bit, but not that much. And again, like the cross polytopes seem to be a pretty good choice, like for dimensions 5, 6, etc., and probably in higher dimensions as well. But evaluating this numerically becomes pretty difficult also in higher dimensions, like in higher projection dimensions K. Okay, so just to summarize the results that I mentioned here, and this is also the last slide, so just to give you an overview of the contributions. So I mentioned 2 contributions which I will which are also mentioned here. So first of all, there's a theoretical framework to test the performance of any spherical code, where we express the collision probabilities that we care about in terms of these multivariate orthogonal probabilities of multivariate Gaussians. This actually allows us to solve the 2-dimensional case explicitly, and we can conclude that the triangle hashing is actually optimal there. And it also gives you a recipe to at least do a numerical evaluation of the exponents rho that you get in higher dimensions. And also we illustrate a survey of various spherical codes that you can use in like 3, 4, 5, and 6 dimensions. And you get some winners out of this, which are mostly like cross polytopes. And this suggests that cross polytope hashing is actually a pretty good choice. So what I didn't mention here is that you can also get some lower bounds for each projection dimension. Like you can say like, okay, if I project down onto a 5-dimensional sphere, like what is the best I can do for partitioning? You can get lower bounds based on like idealized partitions using spherical caps. And also you can, so the last contribution is a more practical comparison of different spherical codes, where you don't only look at parameter rho, but also like at practical costs of projections and how code sizes affect this. And this suggests actually that using the lattice-based hash family, DK is actually slightly better than cross polytope hashing. Thank you for your attention.